Okay, so let's talk about pseudo-differential operators. So we have the class Sm or Sm1 not of classical symbols of order m. Okay, a real number is defined. So it will be the set of the functions px psi, c infinity, rn, rn, so that we will define this p, j, sm is less than infinity for j a natural number, okay, where this p, j, sm, it will be the supremum of the norm infinity psi minus m plus, well, alpha d psi alpha d beta x, okay, so both variables p, okay, and norm infinity of rn such that, well, alpha plus beta is less than equal than j, okay, and this psi between brackets is 1 plus psi squared 1/2. So in classical symbols we're talking about this continuous functions that depends of this p, some kind of norm that we define, absolute value, that depends of what we've been using when we make a transform of the Laplacian, and the derivatives of both variables x and psi. So the pseudo differential operator, let's say psi p, associated to the symbol p in Sm, the set that we just defined, is defined by psi p fx is equal to the integral of inner n e 2 pi ix psi px psi f transform psi d psi, okay, this is with f in the Schwarz space Rn, okay, so the pseudo differential operator will take f in the Schwarz space and then compute, well, we have seen this and this in the anti-transform, and then we multiply by this p that has a property that the norm that we find that has psi multiplied by the derivative in psi and derivative in x with the exponents alpha and beta in L infinity can't be infinity, okay. So for example, a partial differential operator p equal to the sum of the sum of the alphas less than n, a alpha of x functions dx alpha, okay, so these are the sums of functions. These a alphas are in the Schwarz space, okay, and if p is our pseudo-differential operator, its symbol is going to be P of xi equal to the sum, again, alpha as an n, the A alphas and the 2 pi I psi alpha that appears naturally in the transform of the equation, for example, for the transform of the partial derivatives. It will be in Sn. Okay. Okay, so now let's announce some theorem. Not going to prove it, but we have to state them. This theorem is Sobolev boundness. Okay, so M is in R. Okay, P is a symbol in Sm, and S is in R. Okay, so then the pseudo-differential operator psi p extends to a bounded linear operator that goes from hm plus s to hs, always in Rn. Okay, and moreover, there exists J, this is J N M S, and C N M S, okay, such that, okay, so the norm of this pseudo-differential operator f hs is less than equal than c p sm j and norm f hm plus s is a plus. Okay, so we can bound the pseudo-differential operator knowing its symbol. Okay, and well, we'll just have to know S and M to see in which spaces it's going to be out bound. So another theorem, symbolic calculus, let M1 and 2 real numbers, P1 and P2 are two symbols, one in SM1 and the other in SM2. Then there exists P3, that is in SM1 plus M2 minus 1. P4, that is in SM1 plus M2 minus 2, okay, and P5, that is in SM1 minus 1, such that psi P1, psi P2 is equal to psi P1 P2 plus psi P3, and psi P1 psi P2 minus psi P2 psi P1 psi will be equal to psi minus I P1 P2 and this Poisson bracket, okay, and plus CP4, and then another one is that C pi 1 adjoint or conjugated C would be conjugated P1 plus psi P5, okay, always respecting the sets where each symbol P are. Okay, and such that also another condition that for any J there exists J prime, another natural number, and C1, that is a C1 and M1 M2 J, okay, and C2 and M1 J, such that, okay, and now we'll have that let's say with the absolute value of the normal we define P3 SM1 plus M2 minus 1 plus P4 always J SM1 plus M2 minus 2 will be less than equal than C1 P1 J prime SM1 multiplied by P2 J prime SM2. Okay, and this is one, and another one I could write it small here, P5 J prime S and 1 minus 1 less than equal than C2 P1 J prime SM1. Well, just to take in considerations, this is a theorem so that one can manage with the pseudo-differential operators. And just to remember, the Poisson brackets are the sum n j equal to 1 of dxij p1 dxj p2 minus dxj p1 dxij p2. Okay, this was important for the second of the conclusions of the theorem, that we can say that is a relationship between psi p1 psi p2 minus psi p2 psi p1, and this is the commutator, okay, of cp1 cp2, and this is a relationship between the commutator and the psi minus I, and here is the Poisson bracket of p1 p2 plus p4. Okay.